optimal control. And I will give a rough introduction to the learning outcomes we will have for this course. So first, we will familiarize with the state-space representation as a modeling formalism of differential equations. It's important to know what you will get out of this course before you actually start, so you will have a goal. And secondly, the linearization of nonlinear differential equations. Thirdly, we'll derive their input and their state solutions of linear system, and we will compute the state transition matrix. Then we will understand the implications of solution to the stability of the system, and we want to find out the connections between the state space equation and the transfer functions. Then we will analyze structural linear properties, the controllability and observability. And we will derive the minimum energy control loss and design state band. So these are for design purpose. Design the state feedback controllers via pole placement. This is our method. And we will design linear state observer. We will understand the separation principle to perform the output feedback control. And we will use the method called linear quadratic regulator control design. Our course is divided into two parts. One is to introduce linear system, and second one is to introduce optimal control. For linear system, we are analyze them in the time domain, and before we will analyze it in the frequency domain. The analysis complements traditional control design on transfer function, which are basically in frequency domain. And we will represent the linear system in so-called state-space form, which is basically a linear ODE that and algebraic output equation. We will analyze the existence and the uniqueness questions for these solutions, and we will show how to construct solutions to a certain class of linear systems in closed form, and study the properties as far as stability concerned. And we will see how the design controllers can steer the system trajectories to a desired location of the space. We'll get to that later. And for optimal control, we will build the linear system analysis to design the controller for such systems. We introduce different design methods, especially for minimum energy controller, which are open loop. And we will analyze the closed loop with feedback controllers. And finally, we'll design the feedback controllers while optimizing a certain criterion. So next, we will get to know some notations. We will use R and C to denote the set of real and complex numbers. And R to the n, that is the n-dimensional vectors, and R to the m times n, that is n times n matrix. So first we will introduce a simple pendulum motion. In the figure 1, a mass is hanging from a weightless spring with length L, and initially the pendulum creates an angle with the vertical axis, that is theta, and has some angular velocity that's called theta dot, and it is released from its initial position with angle changing, theta changing with time. Okay, so we have our parameter time. We would like to describe the physics that govern the motion of pendulum. So we will have a rotational motion, this is our angular velocity, and times its radius to the center of rotation will get linear velocity, and the pendulum mass experiences its weight mg, as well as a friction force dl theta dot, because the friction force is proportional to the linear velocity, and the d is our friction dissipation constant. By using Newton's law, we will have, this is our ma, that is a force, and this is the resultant force we have. Mg sine theta denotes the gravity force component along the direction of motion. And we can measure the angular position by measuring theta, and which is exactly y in our equation here. For every time instance, the motion is captured by its angular position and the velocity, which is theta and the theta dot. So we set them to become x1 and x2. Remember this, we will always use this later. And notice x1 dot, which is theta dot, equals x2. And we write out its expression will be theta 2 x2 dot equals this expression. And then our measurement equation will compact like this. So basically sub in the values and we will get our y. So first order ODE, and a elliptic system involves a two-dimensional vector xt. The ODE together with the algebraic equation capture behavior of pendulum. Okay, the next concept I want to introduce is autonomous, which is unforced. No external force is applied to the pendulum. We don't consider the gravity as an external force. And the second scenario is an electric circuit. So in figure 2, we have a resistance R in series with L. And there is an external voltage U here, which applied to the system, and we would like to determine the ODE that captures the behavior of voltage VC, which is across the capacitor notices, and the current IL across the inductor. We want both VC and IL to be measured. So this is our goal. And we have the voltage across the inductor is this equation, and the current across the inductor equals the current across the capacitor because they are in series. Therefore, the voltage across the inductor can be expressed as this because we just sub in the values, and we know across the resistor V is equals to Ri. So by Kirchhoff's law, we will get this as the sum of the voltage equals Ut, which is the input, and subbed in those expressions. So we will get a second order ODE with respect to VC. And we want to find VC and IL, remember that. We assume that we can measure both the voltage across C and the current across L. So we will have access to a measurement equation. The fact that we can measure both, notice the both of equation is related to energy. So we rearrange the equation and we will, under our choice, we have IL this, yes, that's right. So here, okay, here x dot is just x1 dot is VC dot, and it will become because IL is x2, so we get the relationship between x1 and x2, and we will express it in a compact form and call that measurement equation. And the first one is the second ODE. So we transformed a ODE to a first order one, but for a lifted system now here. Then we want to express it in state space representation. This is our learning goal. Despite the difference between the physical system, we can capture the behavior by means of similar mathematical expression. So for a nonlinear time varying system is in state space form if it can be represented as x dot t equals fx t u t and t time t. fh's are nonlinear functions of x and u, possibly time t. We refer to, because this is time varying, we refer to the dimension of the state as the order of the system. The function f is often referred as to a dynamics or vector field, and utyt is straightforward. They capture the actuation commands and sensor measurement respectively. And xt represents the state. We will talk about it a lot of times, so it's important to remember. So f does not depend explicitly on time, so we will say that time is invariant. If it depends neither on t nor on ut, we say that the system is autonomous. Memorize this definition, not on t or ut. So the pendulum example is a nonlinear autonomous system. For a time-varying system, we have coefficients matrices. These are all matrices whose entries may depend on time. But for a time LTI, the A, X, B, C, D, these matrices are independent of time. For the electric circuit example, that is a time invariant system. It was non-autonomous because we have an external input. So we can draw out the block diagram for LTI here. We'll have x dot t integrate, we'll get xt, and by a times a and plus ub, we will get x dot, that's exactly right, and for y, we will have c times x, yes, and d times u here, yeah. So we can derive the state space form from the physical description using experience. So firstly, to determine the input variables, it could be external force, or like here, a voltage source or current source. And for the output variables yt, consider sensor output that we can measure. That is something we can measure. For the state variables, these are states. They typically are variables that capture the past and together with the inputs gives information about future from past to future evolutions. Namely x dot. For mechanical systems, these are typically position and velocity components, and for electrical, these are voltage and current. The state variables are often related to storing energy. Describe the physical evolution. For this one, this takes derivative of state variables and exploit physical laws. Not all systems can be written in state space form. So, for example, if we have a delay, then the output equation is represented like this, where Td represents the delay. To determine the output for this system at time instance after t, we need information about the entire input history over the time interval, rather than a point-wise estimate. So in other words, the output function h will need to admit as input functional rather than vector. Such is called infinite dimensional. Okay, so linearization of the vector field f of the underlying physical system is nonlinear. Designing controllers for nonlinear system is a difficult task. So we just do for a linear system. So to this end, consider nonlinear vector field f, and fi is assumed to be differentiable. And for simplicity, we assume it does not depend on explicit time. And we assume that we have access to a non-real state input trajectory. Then we will consider a perturbation set around its nominal trajectory. So this is nominal, and this is a perturbation here. So this will be x star x p, and this is x t. We suppose these perturbations are small enough, so we can employ UPT to ensure that xt remains close to the nominal trajectory. To achieve this, by the Taylor series expansion, around this point, we will have x dot equals fx ut, and we plug in the values here, and we use Taylor series expansion, we will get this equation. And the higher orders, we sum it in this term. Neglecting higher orders as the perturbations have been assumed to be small enough. Okay, so this can gone. Then since x star equals this one, then we will minus this star, and for the right hand side we will be left with these two terms. This is what we are given before, and as f is a vector, the partial derivatives respect to x and the u are given by this big matrix. The resulting perturbation dynamics form a linear time varying system. So consider the nonlinear system x dot fx dot u, and the functions comprising f are differentiable. The linearization of the system around a nominal trajectory is given by the linear time varying system. So here A and B are matrices in terms of t, time invariant system. And here we have AT and BT equals this partial differentiation because we derived it before. And to look at one example, consider state space representation of pendulum linear as a system around the nominal operation point. And this is an autonomous system, so no input appears, no external force. So we will get these two expressions. By state space representation of the pendulum, we have f equals f1, f2x, and the linearization of the system around the nominal operating point is given by this. Okay, then we will perform a small angle approximation. So let's make a summary to this chapter. This chapter introduced state space, and in particular we discussed the means of examples. Nonlinear time varying system, f and h are nonlinear equations, and linear time varying system where these are entries depend on time. Linear time invariant, so these matrices are independent of time. We detail this procedure as linearization that allows approximating locally behavior around the nominal trajectory. This is a useful thing by a time varying linear system. If rather than a nominal trajectory, we have an operating point. Change the color. Okay, this is our first tutorial. Let me end like this, and I hope you enjoy and share.